Hello everyone, as we have seen in the previous section about the basics or fundamentals of phase equilibria and the thermodynamic concepts of phase equilibria. In this section we will see or we will apply the phase rule and this fundamental concepts to one component systems like water and sulfur systems. Before that we see a general one component system, how a phase diagram look like. A phase diagram is a plot of pressure and temperature to see how the pressure conditions and temperature conditions depend each other during phase transition. Here it marks a very simple phase diagram with three phases, 1, 2 and 3 phases axis in equilibrium like this. Along this curve, along this part of the curve, the phase 1 and phase 2 are in equilibrium through a phase transition process which convert phase 1 into phase 2. Likewise, here the equilibria is between phase 1 and phase 3, and along the curve at this given, for example, at this given condition of temperature and pressure, the substance converts from phase 1 to phase 3 and vice versa. And likewise, here in this curve, you have got equilibrium between two phases, phase 2 and phase 3. And along each curve, and there is a point, a junction of the three curves, and there are areas under the curves, and along each point, each curve and each area we learn to apply the phase rule. That is what we will do in case of water and sulfur system now. So coming to water system, water exists in three states and three phases, mainly vapor, liquid and solid phase. So to start with, at the high condition of temperature and pressure, this actually marks the critical temperature pressure conditions for conversion of liquid water into vapor water, or the vice versa, to convert vapor water into liquid water. So at this point A, the vapor water and liquid water exist in equilibrium. And as you move along the curve AO, you can see that this vaporization curve, this is the vaporization curve, and on both sides of the curve are liquid and water vapor, and you see this vaporization or the boiling point of water decreases as the pressure decreases. Along the x-axis, down the y-axis you have decrease in pressure. So as you decrease the pressure, the temperature also decrease, that is the boiling point also decrease. So the curve OA marks the boiling point of water at different pressures. So that is why it is the vaporization curve with the equilibrium between liquid and water vapor. And at point O, you can see the appearance of solid water. Water starts to solidify, and OB marks, this curve marks the solidification or the equilibrium between solid on one hand and liquid on the other hand. So this is the melting point curve of water. So OC, here you can see the equilibrium is between solid water on one hand and vapor water on the other hand. So this is the sublimation curve. OC will be the sublimation curve. So this is a very simple form, the phase diagram of water, and you can see supercooling. Even if you cool below the freezing point, very slowly you can observe occurrence of still water phase without the formation of a solid phase. That is what is known as supercooling. And along OC, you will not see equilibrium between solid and vapor, but instead you will see equilibrium between supercooled water and vapor. So this is a metastable equilibrium. The OC dash marks the metastable equilibrium. And now we can see this junction, the junction O between the curves AO, BO and CO marks with this 58 millimeter pressure and 0.0099 degree centigrade temperature. At this point, you can see both liquid, vapor and solid, all the three phases exist in equilibrium, and this coexistence of the three phases is marked by triple point. This junction O is called triple point, and at triple point you can say, if you apply the phase rule F, this equation on this triple point, here the system is one component, only one component is there, so C is 1. P is 3 because the three phases exist in equilibrium. So if you apply these values here in this equation, you can say that the system is invariant, that is the degrees of freedom will become 0. That is, you don't need to mention especially pressure or temperature. You don't need to mention any of this parameter to explain the point O, because it is obvious it has got a fixed value of 458 millimeter and this much of temperature. It is fixed value. You don't need to mention this in special. You don't need to mention any intrinsic variable to explain this point. That is why the system is invariant with a 0 degrees of freedom. On the other hand, let's consider one of the curves. Let's say OA. If you consider the curve OA marks the equilibrium between vapor and liquid. And if you want to explain any point on OA, let's say this point on OA, you can see the degrees of freedom. If you calculate the degrees of freedom, again the number of components is 1 and P is 2 because the two phases liquid and vapor are in equilibrium. So P will be 2. Now you can say that your degrees of freedom will become 1 if you calculate. F will be 1 minus 2 plus 2. So degrees of freedom will be 1. That means the system is univariant. That means to explain exclusively this point, you need to mention either pressure or temperature. One of those values is necessarily required to explain this point, explain any point on any curve. So any point on any curve will be univariant with the requirement of either pressure or temperature to be mentioned to understand that point. On the other hand, if you look at any area, let's see this area BOA. The area under the curve BOA marks by the presence of liquid water. In this area, you have got only liquid water. Likewise, AOC has only vapor water and COB has only solid water. So considering any of this area, let's say AOB, where only one phase called the liquid is present, so P will be 1 here in this equation. So you can say F will become 2. That is, in this equation you get the system as bivariant, degrees of freedom is 2. That means to explain any point under this area, you need to mention necessarily both temperature and pressure to explain this point. That is why the system is bivariant. Two parameters are required to explain these points. That's how you understand the variance or degrees of freedom of the system in phase diagram. Okay, so this is about the phase diagram of water system. Now we will see another single component system, which is sulfur system. Sulfur has got additional phase transition than water. That's why we see this especially. Starting with the curve AB, the curve AB marks the presence of solid sulfur, that too exclusively the rhombic crystalline form of sulfur. So this form one phase, the rhombic form. We have seen this in the previous lecture that a rhombic and monoclinic phase undergo a phase transition from crystalline transition from rhombic to monoclinic at certain temperature pressure conditions. Okay, coming back. The curve AB marks the conversion of rhombic sulfur, the solid form, into vapor form. So this will be the sublimation curve of a rhombic sulfur, where the rhombic and vapor sulfur exist in equilibrium. As you increase pressure, you can see the sublimation point also increases. And at B, what happens is you have monoclinic sulfur start to appear, that is at B along the curve BE, the rhombic sulfur is converted to monoclinic sulfur. So on one side of BE you have got a rhombic sulfur and on the other side of BE you have got monoclinic sulfur. This crystalline phase transition occurs along BE and BC will be, therefore, here above BC you have got only monoclinic sulfur now. So the curve BC marks the equilibrium between monoclinic sulfur and vapor sulfur. So that is a sublimation curve of monoclinic sulfur. And EF, this point, from this point E, you have got like BE, you have got rhombic to monoclinic conversion. Above E, you can see the rhombic sulfur directly converts to liquid without the formation of monoclinic. Okay, so EF marks the conversion of rhombic sulfur to liquid, that is the melting curve of rhombic sulfur. And likewise, Ce marks the melting curve of monoclinic sulfur, and beyond C, that is, if you go along CD, you can see here you have got only the liquid vapor sulfur. You can see the vapor to liquid conversion. Below CD you have got vapor sulfur, and above CD you have got liquid sulfur. So the liquid to vapor conversion occurs along CD. And there are three triple points. The triple point B, the first one marks the presence of rhombic sulfur, monoclinic sulfur and vapor sulfur. And the point C marks the presence of vapor sulfur, monoclinic sulfur and liquid sulfur. Likewise, the point E, the triple point, the third one marks the presence of rhombic sulfur, liquid sulfur and monoclinic sulfur. So this is about the phase diagram of sulfur system. And again, as we have seen for water system, you can say for every triple point you will be able to calculate there the degrees of freedom will be 0, that is, the system will become invariant. And along each curve, on any point on each curve, you get the system as univariant as explained before, and each area will give you bivariant system, that is, system needs both temperature and pressure to be mentioned in any of this area. Okay, that's about the sulfur system. With that, we end this session, and in the next session, we will see two component systems. There are two types of two component systems. The first one is simple eutectic system, that is, system without formation of any new compound inside, whereas there are other compound forming system, that is, two components A and B react to give you new component AB. So we will see that in the next session. Until then, thank you.